rotating horizontal turntable. It slips when its speed is 50 centimeters per second. What provides the force in the radial direction when the coin is stationary relative to the turntable? So we have a turntable. Do any of you recall what a turntable actually is? Yeah, it plays those vinyl things that are kind of big like this, and you put a needle on it, and the needle plays music. I may be dating myself, but we used to call those record players. And such a thing was a turntable. So a few of them might still exist, and we might put it to use by putting a coin on the turntable to rotate it around. And the first question was, what provides the force in the radial direction when the coin is stationary relative to the turntable? What provides that force that keeps it moving around in a circle? Good answer. Friction. Why couldn't I say centripetal force? It's all a matter of semantics, but why couldn't I use the phrase, why couldn't I say the centripetal force is keeping it moving around in the circle on the turntable? Was that good? The coin is stationary, but it is stationary relative to the turntable, but it is moving around in a circle in our environment.
But there's nothing. If there wasn't any friction, you apply a force in the coin to just keep going.
That's right. I think the point I'm trying to make is just that there's a difference between saying net force and identifying the physical force. In other words, our centripetal force, which we defined the other day, which is the mass times the centripetal acceleration, that is a net force. That's your net force. And that is the summation of all the forces acting on the object. But that could be anything. All right? When you're talking about net force, anything could be supplying, and it could be more than one thing, supplying eventually that net force. So it's not really, the centripetal force is not really an entity in itself. It's not really a physical thing in itself. It's equal to all those forces that may add up to it. And in this case, it would be static friction. So without static friction, which is the physical force, then this coin would go flying off in a straight line direction. So I just want to make that point because it helps you, if you can realize that, it helps you to approach centripetal force problems because they're just like, in a sense, the other force problems that we've been doing, where we find the net force over here, and then we set that equal to ma, and ma is this, where a is the centripetal acceleration. Right? So ma is not itself a physical force. It's what we set everything else equal to. All right? So after that, the static friction that's applying this force, and in this case, we're looking down from the top. So really, this is on a flat plane, and so our normal force on this coin is going to be equal to its weight, mg. So the static force is friction, and that's going to be equal to mu times the normal force, which is mu times mg in this case. So we're going to have our centripetal force equals mu mg. And so for that matter, the mass of this coin is not going to figure in because we can cancel out the mass on both sides. And the question is, what is the coefficient of static friction between the coin if I solve this for mu, since v squared over r is mu g, then the stack coefficient of friction will equal v squared over gr. And we're traveling at 50 centimeters per second, it would be 0.5 meters per second squared over 9.8. Radius of that circle is 30 centimeters, 0.3. And I never have these worked out. Somebody work this out? Come up with that? I got that 0.085. That's pretty slick turntable. 0.085. Yeah, that's one. Let's take a look at number 3 on the example test as well. One right before that. One we just did. We haven't done anything like this. 3 masses are connected on the table as shown. The table has a coefficient of sliding friction of 0.3. 3 masses are 3 kilograms, 2 kilograms, and 6 kilograms respectively, and the pulleys are frictionless. Determine the acceleration of each block and their directions. So I have a table. Two pulleys. We have mass 1 over here, which is 3 kilograms. Mass 2, which is 2 kilograms. And mass 3, which is 6 kilograms. And we're told that there's a coefficient of sliding friction between the block and the table of 0.3. That means the frictional force up there is 30% of the normal force on that block. The other 2 blocks don't have any friction, right, because they're not sliding or anything. All right, and the first question is to find the acceleration. What should I do? Blob method. Try blob method. We'll try this whole thing and treat it like one system, so we don't have to worry about the separate tensions in the core. There are the tension 1 and the tension 2, but if I make that part of the internal system, then we're just going to worry about this whole thing. And I have a pretty good idea, since this is 3 kilograms over here, and this is 6 kilograms over here, that this whole thing is going to move like this. All right, so this is going to move around like this with 1 acceleration, and this is going to move up around like this with 1 acceleration, and mass 2 is going to move to the right. So I treat this all as one mass, and then look at the external forces acting on this one mass. And what we have is we have the weight of mass 3 over here, which we'll call M3G. That's kind of pulling it forward. And then we have the weight of mass 1 over here, M1G. That's kind of slowing it down a little bit, because this is pulling it forward, and this is kind of slowing it down. And we have one more force that is affecting the motion of this whole system, and that would be the friction on mass 2 up here. In order to figure out what that is, I might quickly just realize that it's got weight, M2G, it's got a normal force, N, and the frictional force is proportional to N, which is equal to M2G in this case. So we'll have a frictional force going against the motion up here, F, and that's equal to mu times normal force, which in this case would be M2G. So we'll have a frictional force, mu M2G, against the motion up there. sliding friction always acts against the motion. Sliding friction. And that's what we have here. Other kinds of friction can kind of help, aid you. Like I was saying about walking, when if I push this way, friction will actually push me forward. And so that can kind of aid me. Okay, so let's set up Newton's second law for this whole system. We've got, let me redraw it just to make it a little clearer. We've got this one system moving like this. Total mass, 3, 2, 6, 11 kilograms. We've got one force making it go over here, M3G. Another force slowing it down over here, M1G. Another force here, slowing it down as well. The frictional force, which is mu, M2G. As a result of these three forces, at least in the line of its motion, it manages to accelerate forward like that. So setting up Newton's second law for this, I would say that the total mass times acceleration will equal the net force in the direction of acceleration, which would be M3G minus M1G minus mu M2G. So the weight of mass 3 minus the weight of mass 1 minus the frictional force. Why don't I include M2G itself, the weight of mass 2? It's balanced by the normal force and? Yeah, it's perpendicular to the direction we're going. So it's transverse to the direction we're going. That's 90 degrees, from that direction. We're moving this way up there. And so they balance, and it's not really affecting the forward motion, except for the fact that it involves in friction. All right, so this is what I have. Let's solve for the acceleration. We got 11 kilograms times A equals 6 kilograms times G minus 3 kilograms times G minus mu, which is 0.3, times 2 kilograms times G. So I have acceleration, we equal 6 minus 3 minus 0.6 times G over 11. So it's going to be 2.4 times 9.8 over 11. Thank you. 2.14 meters per second squared. So that is the acceleration of this whole system, and we were asked to find the acceleration of each mass. So if I want to be totally complete, I could say that for mass 1, this acceleration would be going up. For mass 2, this acceleration is going to the right. And for mass 3, this acceleration is going down. It's the same acceleration for all three, at least in magnitude. Question B, what is the tension in each core? How should I go about that? Free body diagram. It sounds like a great idea. Of? Okay. Let's take the second one. M2? Third one? Third one? Yeah, let's do the third one. We could do the second one, but that's going to be a lot more work. So let's focus in on, say, mass 3, or even, let's start with mass 1, actually. What do you think? Sound good? So let's do a free body diagram of mass 1, 3 kilograms. Let's label all the external forces acting on it. Of course, there's only 2. We got weight, M1 pulling up, and am I done? Let's indicate acceleration on this. It happens to be actually going up with a value of 2.14 meters per second squared. That is my free body diagram, and the purpose of that, the main purpose of that is to help me set up Newton's second law for the motion of that mass. So looking at my free body diagram, I have two forces with a net force in the direction of the tension 1 going up. That's my acceleration. So I could say that the summation of all the forces, in this case in the y direction, will equal the mass times acceleration, m1a, and that is equal to the net force in the direction of that acceleration, which will be T1 minus m1g. We know acceleration, we found that. We know mass 1 and we know g, so we can solve this for tension. So we'll say tension 1 is equal to m1a plus m1g. So that's going to be equal to 3 times 2.14 plus 9.8. Just factoring out the mass, and that comes out to 35.8 newtons. So that's the tension in the chord 1, the chord on the left. We want to find the tension in the other chord, so let's do the same thing with mass 3. Mass 3 is 6 kilograms. We're going to do a free body diagram of mass 3. It's got weight going down, equal to m3g. There's a tension going up. Would that tension be the same as tension 1? Not necessarily. I mean, it's not necessarily the same as tension 1. In fact, it most likely is not the same. So, actually, to be honest with you, it probably would never be the same. So, that's tension 2. And as a result of these two forces, it manages to accelerate down with a value of 2.14 meters per second squared. So that's our free body diagram for mass 3. Helps us to set up Newton's second law for that mass. And so we'd say that the summation of all forces in the y direction is equal to, not 0 because we're accelerating, but mass 3 times acceleration. And that's equal to the net force in the direction of acceleration, which would be, thank you, m3g minus tension 2. Let's use this to solve for tension 2. Let's bring tension 2 over to the left, m3a over to the right. So our tension 2 is equal to m3g minus m3a. It's going to equal mass 3, which is 6, times 9.8 minus 2.14. That is 45.96. So we'll round that up to 46.0. 46 newtons for that tension. Part C, if the mass is started from rest, what's the velocity of the 3 kilogram mass after 2 seconds? How would I do that? Kinematics. So kinematic equations will never leave you. Right? You should probably memorize them because they will pop up when you least expect them. Even in physics 2 or physics 3. So just go ahead and memorize them. Or make sure there's a significant spot on your card. So this one, they start from rest. What's the velocity after 2 seconds? So our initial velocity is 0. Time is 2 seconds. Acceleration, very good. Acceleration 2.14. And the question is, what's the velocity after 2 seconds? So there we have it. There's our 4 variables that we need. Velocity equals initial velocity plus acceleration times time. Start from rest. So that's just going to be 2.14 times 2, or 4.28 meters per second. That would be the velocity of all the masses after 2 seconds. So mass 1 will be going up with that speed, 2 across with that speed, 3 down with that speed. They're all connected. Sound good? I can put something like this on the test. I've already had requests for number 5. On this sample test, number 5 is by far the hardest problem on the sample test. It would constitute, it would constitute what might be an extra credit problem on this test. So let's look at 5 and let's see what we can do with it. A block of mass 2 kilograms is held in equilibrium on a frictionless incline of angle 60 degrees by the horizontal force F as shown. Determine the value of F. So here's an incline, 60 degrees. We've got a mass up here on this incline, 2 kilograms. And we have a horizontal force pushing on it like that. And as a result of all the forces acting on that mass, it doesn't move, so it's in equilibrium. So Newton's first law would apply in all directions. We want to find the value of F. So I'm going to proceed with this, and the first thing I'm going to think of to do is free body diagram. Now, on a test, I probably won't even ask you to do that. I probably won't say, show a free body diagram. I might, but it's probably something you want to do anyway, because it's really hard to proceed and set up your equations unless you do the free body diagram correctly first. So let's do a free body diagram of this mass. It's 2 kilograms. We want to label all the external forces acting on it and try to set them up in a convenient coordinate system. So what forces do I have acting on this mass? I got mg, I got gravity, which is pulling down straight to the center of the earth. And I actually want to deal with it along this incline. So I'm going to break it up into 2 components. And we've seen that if we break it up into 2 components, there's going to be one component down the incline equal to mg sine theta. And there's going to be another component into the incline equal to mg cosine theta. Are you convinced that that's the way those components should be? We've proven that before using geometric considerations. So I guess you can just accept that, right? So that's kind of nice, because we're gonna say that x is down the incline, y is perpendicular to the incline. That's going to be our new coordinate system. Now, what else do I have? The normal force. All right, I have a normal force that's normal to the surface. That's coming out this way. We'll just call that N. Always perpendicular to the surface, so that's cooperating. That's totally in the positive y direction. And the force F, which is going horizontally, that is not cooperating with my coordinate system. It's going this way, like this. So I need to put that in terms of x and y in order to make it work for my coordinate system so I can set up my equation. So what I'm going to do is I got F going totally horizontal. I'm going to break it up into two components. It's going to be one component that's going to be up the incline, and another component that's going to be perpendicular into the incline like this. These two smaller components constitute a right triangle here that add up tip to tail to make this longer vector. So this plus that equals that longer vector. And this is a right angle here. So in order to set up and figure out what these components are, one up the incline and one into the incline, I need to find out what these angles are, all right, in this right triangle here. Well, if I look at this incline, the incline angle is angle theta down there, which happens to be 60 degrees. Now, if I look at the way this triangle is set up, this force F is totally horizontal like this, and the ground is horizontal like that. So we've got two parallel lines there, if you can imagine them. And I've got one line intersecting those two parallel lines, and so this angle right here should be the same as this angle up here. In other words, it should be the same as this angle right here. That's theta. All right? Just by using geometric concerns. So if that's theta, that means in this particular case, the component of F that's up the incline would be F. What was that, Kristen? Sine theta?
No,
Cosine theta? We're adjacent to the angle. So it is cosine theta. F cosine theta. And then the one into the incline will be F sine theta. It's a little tricky because it didn't break up the same way that the MG broke up. All right. Because the MG had to be going straight down, not horizontal, when we first had it. Okay, so there we have it. I think that's it because no friction. We didn't have to deal with friction. So here's all of our forces. We may wish to redraw it just to make sure we've got everything in the right direction. So here's our mass, M 2 kilograms. And here's our coordinate system. X down the incline, Y perpendicular to the incline. And if we look at all of our components of forces, we've got one force down the incline, mg sine theta. We've got two forces into the incline. We have an mg cosine theta and an f sine theta. And we have a normal force perpendicular to the incline out that way. And we have one force up the incline, an F cosine theta. As a result of all these forces and these components, it doesn't move. And the first question in this problem was, what is the value of F? The easiest thing for me to look at would be along the x direction, because I actually know what M is, so I can figure out mg sine theta and compare that to F cosine theta. So if I look and sum up all the forces in the x direction, that should be 0 because it's not moving, no acceleration. And I did say down the incline, doesn't really matter. Okay, so let's just go with what I said. let's go down the incline. So we'll say mg sine theta minus f cosine theta. Should be 0. So we'll go positive down the incline, and opposite that would be negative. Solve this for f. So we have f cosine theta equals mg sine theta. Divide both sides by the cosine of theta. We have f is going to equal mg sine over cosine tangent theta. And so that would be 2 kilograms times 9.8 times the tangent of 60 degrees, 19.6 times the tangent of 60. What is it? 33.9 newtons. So far, so good. Part B says, determine the normal force exerted by the incline on the block. If I look at the y direction, there is no movement in the y direction, so Newton's first law applies there. The summation of all the forces should equal 0. But we do actually have forces, but they're just canceling out. And in my positive y direction, I have the normal force. That's going to be a positive force. And then I have two forces going the other way. I have a mg cosine theta. And I have a f sine theta. So solving for the normal force, I'd say the normal force is equal to mg cosine theta plus f sine theta. Normally we would have just n equals mg cosine theta, but now, because we're pushing on this block, we're actually pushing the block into the incline. And the incline is pushing back a little bit harder because we're pushing it in, and hence the normal force is greater than the weight. It'd be analogous to if you were standing around and somebody came along and started pushing you on your head, pushed you into the ground a little bit. The normal force of the ground would be greater than your weight because it would be equal to your weight plus whatever force they were pushing you with. Right? It would still offset everything that you're pushing into the ground with. Something my brother used to do. So I know this from experience. Right? That's why I'm a little bit shorter than he is, because he used to always push me down. But more about that later. So if we put in the numbers here, we have 2 times 9.8 times the cosine of 60 plus our newly found F force, 33.9, times the sine of 60. If I put all that together, I get 39.2 newtons. So that is our normal force. So not so bad. If it says a good free body diagram, then your equations should follow pretty logically from there. Part C, if the force F were removed, how far would the block move in 1 second? So if I were suddenly to take away that force F, the block's going to start moving down the incline. How is it going to move down the incline? Under what acceleration? There's going to be a force on it, and the only force on it would be mg sine theta down the incline. In other words, if I remove that F force, all of a sudden there's going to be a force down the incline by itself of mg sine theta. So I could say that it will accelerate down the incline under this one force. According to Newton's second law, then I would say that ma equals mg sine theta that's it, because the force F is removed. Masses cancel out. So the acceleration down the incline would be just g sine theta. So acceleration will equal 9.8 times sine of 60. 8.5? 6. 8.48. Wow. That's a pretty steep incline, so that's pretty high acceleration. So the rest of it's kinematics. How far would the block move in 1 second? We're going to the acceleration, 8.48 meters per second squared. What else do we know? Time is 1 second. Initial velocity is 0. And we want to find delta x down the incline. So we'll say that displacement equals initial velocity times time plus 1/2 acceleration times time squared. Initial velocity is 0. So this will be 1/2 times 8.48 times 1 second squared. 1.24 meters. Part D, was the work done by gravity? And this time we haven't talked about work yet. So, let's save that idea until I have a chance to talk about work. Can I talk about it? Yeah, let's save it. All right, so what do you think? Did you have a chance to look at this chapter 6 handout at all? Is that force times distance? That's chapter 7 stuff. Yeah, you went a little bit ahead. Anything in this chapter 6 handout that you want to look at? Centripetal force stuff. All right, let me select a couple of them. Look at number 4 on this handout. A 30-kilogram child rides on a circus Ferris wheel that takes her around a vertical circular path on the radius of 20 meters every 22 seconds. What is the magnitude of the resultant force on the child at the highest point on this trajectory? There's the fourth column on the chapter 6 handout. We have a Ferris wheel. The child on top of the Ferris wheel, and her mass is 30 kilograms. And the radius is 20 meters. Let's see the little arc of this. And she's going to go around the circle at constant speed every 22 seconds. So the time period is going to be 22 seconds. And the question is, what is the magnitude of the resultant force on her at the highest point of the trajectory? find her speed, right? Her total distance traveled will be the circumference of this circle. So we can say that her total displacement will be 2 pi r, and that would be equal to 2 pi times 20 meters, which would be 40 pi, which would be 120 something meters. 125.66, we'll say 125.7 meters. And she's going to do that in 22 seconds, and she's moving at constant speed, so she has a constant velocity of displacement over her time, which would be 125.7 meters over 22 seconds. .71 meters per second. So she's traveling at a speed of 5.71 meters per second. Now when she gets to the top of this trajectory on this Ferris wheel, she's still moving in a circle, but if I were to do a free body diagram on her, it would look something like this. She's got two forces acting on her. She's got her weight is going down, and she's got the normal force, the C, which is actually pushing up. Yeah, actually, she's got a little bit of a normal force. It's actually pushing up. Not like she's not. Is she upside down? I mean, if you're in Ferris wheel, you're actually right side up, hopefully, right? There used to be those Ferris wheels where you had to turn like you're in a cabin and you had to turn the wheel in order to keep yourself right side up, otherwise you'd be upside down. So forth. And as a result of all this, she'll have a centripetal acceleration towards the center of that circle. So if I were to set up Newton's second law for this, I would say her mass times the centripetal acceleration would equal the net force in the direction of the acceleration, which would be, in her case, mg minus the normal force of that c. So I would say that the centripetal force, mass times velocity squared over r, would equal mg minus normal force. However, the way that this problem is stated, it says, what is the magnitude of the resultant force on her? Now the resultant force is her weight minus the normal force. That is the resultant net force. It's also, in this case, the magnitude of the centripetal force. That is the resultant net force on her. So it didn't ask for specifically what the normal force was or what the weight was. It asked for the net force. So we can get it directly by just finding the centripetal force, which is the net force, the resulting force in this case. So I actually did a little bit too much there, but it kind of helps because we're going to be doing problems where we have to kind of set it up that way. So in this case, her resultant force, her net force, is just going to be the centripetal force. And that's going to be 30 times 5.71 squared over the radius of the circle, 20 meters. I got 48.94. 48.9. So I guess we choose A, 49 newtons.
I didn't mean he was off. I did not recognize that he was 50 pounds. And I'm supposed to be 40 pounds.
Right. Yeah, if the seat were to turn, you could be upside down, and the normal force would help you in terms of staying within the circle. It wouldn't help you in terms of staying in your seat. But, well, yeah. So hopefully you'd be going faster then, so that you're, in the sense your centrifugal force would keep you vertical. We used to have a commercial, it was, just a few years back, I don't remember how long back. They had I think it was a Mountain Dew commercial, when they were showing somebody in well, there was two commercials. One was in a roller coaster, where they had a drink in their hand, and when they went upside down, in order to maintain the drink in their hand, they turned the drink over. Let's say they were upside down, so they turned the drink right side up so that it wouldn't spill. And then they came right back in and they turned the drink back again. That's what makes that funny, is that you know it's not true, right? That's against the laws of physics. I mean, if you had a drink in your hand, then whatever's in the drink is doing the same thing as you. So that if there was some centripetal or force as you're going through a circle, and you're pushed against the side of that, so is the fluid in the drink. Of course, the fluid kind of sloshes around, so it probably would spill anyway. But you wouldn't have to turn it against gravity because you're afraid that it's going to spill because of gravity, right? There would still be a net force on it due to everything else, like the forces on you yourself. So, there was another one where I think they're in a truck and they hit something and they spin upside down, and they did the same thing. They turned the drink so it wouldn't spill, and yeah. So I look at that and funny stuff. There's a lot of things that are kind of funny because they play on your intuition of physics, and you know that it's just not true. So I need a collection of those commercials. Where was I? Let's do another one of these, and then let's look at some new stuff. Speaking of roller coasters, take a look at number 7. A roller coaster car has a mass of 500 kilograms. When fully loaded with passengers, the car passes over a hill of radius 15 meters as shown. At the top of the hill, the car has a speed of 8 meters per second. What is the force on the track on the car at the top of the hill? Force of the track on the car at the top of the hill. But here's the track, radius of 15 meters. And we have a car at the top of the hill. Coaster, and everybody's enjoying it. Of course, all my stick figures have that runs up in there like that, so everybody's happy. And the total mass of this is 500 kilograms. The car has a speed of 8 meters per second. This one says, what is the force of the track on the car on the top of the hill? So it's not asking for the resultant force or the net force. It's asking for the specific force. In this case, we could say it's the normal force of the track on the car. So it's kind of similar to what we did here, only we're going to actually have to look at this free body diagram. Let's do that. We did a free body diagram of the car. The mass is 500 kilograms. It's got weight, mg, pulling down towards the center of the earth. And there's a normal force of the track on the car actually going up, like that. And that's it. Those are all the external, real forces that are acting on the cart at this time. But there is a centripetal acceleration due to the velocity of the cart moving in a circle towards the center of the circle. So there's centripetal acceleration going down like that. That's our free body diagram like that. As we set up Newton's second law for that, we say that the mass, let me even be more rigorous, summation of all the forces in the y direction will equal the mass times centripetal acceleration. And that will equal the net force in the direction of the acceleration, which would be mg minus n. Let's solve this for n. So n will equal mg minus mass times centripetal acceleration. So that's going to be mg minus mass times velocity squared over r. That's the centripetal acceleration. Let's put in the values here. This will be 500 times 9.8 minus 8 meters per second squared over 15 meters. So that is 2,767 newtons. That is the force, so we could say that would be D 2.8 kilonewtons would be the force of the track on the car. That time, the normal force. That's going down. You can see that if we get faster and faster, then this normal force will go down and down. Right? As this speed increases here, then we'll be subtracting more and more from 9.8. So there might be a point where this term would actually equal 9.8, at which point, when you hit the top of that track, you will feel weightless for that moment. Because there will be no normal force on the cart at that moment. So it'll just be the same as if the cart were out in space. You would feel like you were weightless.
Is it like when they're trying to make it out how it goes?
Yep, it's like when you're driving a car and you're going over hills and you hit the top of the hill, and sometimes you actually feel like you jump out of the seat, and for a moment you're actually weightless. Right? You're driving fast now.
So the track on the car is normal force,
Yes, in this case,
same direction.
right, normal to the track, because we're looking at this interface between the track and the car. So yeah, it's the normal force of the track on the car. So the car's weightless too. Momentarily. All right, ready for something a little bit new? Through this chapter 6, we've been, well, first thing we looked at was kinematics, which is study of motion, empirical study of motion. So it's just the study of motion, describing it through those 5 kinematic equations, not necessarily knowing why those equations work, but they just happen to work. So it's just the, saying these equations work, this describes motion. And then we proceeded into dynamics, so we studied forces. We said forces are the cause of this motion, and we looked at, vectors and side forces, and we looked at dynamics in general for the cause of motion. Starting with this chapter 7, we're going to approach dynamics in a slightly different way. We're going to use laws of conservation in physics, mainly the law of conservation of energy. And we're going to approach dynamics from an energy perspective. The advantage of this is that if you set up certain problems in an energy way, and use this idea of conservation of energy, then you don't have to worry necessarily about time. Right? Because if you look at 2 points and you say that energy is the same in 2 points, or at least you can compare the energy, then you don't have to worry about when those points occurred, like which one came before the other, or what happened in between. You just have to look at 2 points, evaluate energy here, evaluate energy here, and compare the two. And so it gives you a new way to look at dynamic problems. And so some of the problems that we've already done, using forces and causes and motion and kinematics, we'll be able to do using energy, but probably in an easier way in some cases. Just another way to look at it. So, if you can master chapter 7 and chapter 8, mainly chapter 8, because 8's going to sum it all up, then that will give you a big advantage in dynamic problems. All right, so it's a very good chapter. 8 will not be on this test, so it's going to be on the next test. So we're really going to get into these energy problems after this next test that we have. But to get there, let's talk a little bit about energy. We have energy all around us. It's in different forms. It's present in the universe in various forms. Mechanical energy of things that are moving, or stored energy within springs or anything like that, in a mechanical sense and a macroscopic sense, what we deal with on an everyday basis in our lives. Electromagnetic energy, there's energy associated with light and electromagnetic fields. It can be stored in the field in terms of magnetic energy, it can be stored in the field in terms of electrical energy. Even light itself has energy proportional to its frequency. And so we have energy associated with electromagnetic field. Chemical energy, there's chemical energy stored in the chemical bonds between molecules and between compounds. And basically that would be the energy that we would utilize when we eat something and break down energy for the uses of our body. Thermal energy, there's energy associated with temperature, just the movement of molecules moving around, and they transfer energy by collisions, and that energy is interpreted as thermal energy. Nuclear energy, there's energy associated with the bonds in the nucleus of the atom. That's associated with what's called the strong nuclear force, and if you break that force, you have a lot of energy available to you. But here's an idea. We have all these forms of energy, and we can basically say that one form of energy can be converted to another form. So we can go from one form of energy to another. Now, the progression is easier if you go from what we call a higher form of energy to a lower form of energy, but you can go from lower to higher if you want to expend more work or more energy in doing so. But you can convert from one to the other. Well, here's a statement. It's called the conservation of energy. And it says energy is neither created nor destroyed in in the universe is simply transformed. This is a strong statement. It says, in the universe, energy is neither created nor destroyed. It's simply transformed. So any form of energy you see, and you see it utilized, is not destroyed necessarily. That quantity of energy that you see being used, not destroyed, is redistributed as different kinds of energy. When it's redistributed as new energy, or a different form of energy, it becomes less useful. So the idea is that you have a higher form of energy. It's not destroyed, but it gets distributed in a less useful form as a progression of time, or progression of utilization. It's always transformed to less useful forms, but the total energy of an isolated system is always constant. These are laws of nature. They are laws of physics. A law is a observation, observation of billions of people over millions of years, over billions of observations in their lifetime, that no one in the history of humankind has ever seen a violation of these laws. So it's a law, actually the first one, energy is neither created nor destroyed, it's simply transformed. The first law, that is the first law of thermodynamics. Energy is neither created nor destroyed. So we're not going to really get into it in this course in that sense, because that's not the subject of this course. Thermodynamics would be the subject of Physics 3. So if you ever take Physics 3 in the summer, then you would learn about that. The second statement, it's always transformed to less useful forms. That is the second law of thermodynamics. It's called the law of entropy. And it's a law that says that as time progresses, whatever energy you have will transform into other energy, but it will always be transformed into less useful form. Right? In other words, by the course of that, the universe is becoming more disordered. If you see you have higher form of energy at one point, and then after time it's a lower form of energy, it's become more disordered. It hasn't destroyed the energy, it's just become more disordered. So in a philosophical sense, this is kind of interesting. It's saying, these two statements are saying, first of all, that the energy we have in the universe is the energy that we've always had, is the energy that we will have, that there's no energy extra being created or destroyed right now. So everything around you is the amount of energy that we have, including mass. Mass is energy as well. And then the other idea is that we can measure time, because if we were to measure the amount of energy at some point and the forms that it's in at some point, and we look at another point and we find that it's on the totality of things, it's in a lesser form, then that's at a later time. So from the second law, we'd say that time progresses, the universe becomes more disordered. I'm not going to expand on that too much today, because again, that's not the subject of where we're going with it, but that is thermodynamics, and those are laws of nature. So they've never been observed to be violated. If someone came into you, if you got a job at the patent office, and it's your job to evaluate new machines, new ideas, new patents, someone came in to you and had this big box, this big machine, and said, this is my invention. It takes in a certain amount of energy, but it puts out more energy than it uses. So that actually creates energy. You said, oh, that's interesting. So you open up your drawer, pull out your big stamp, and say, rejected. Okay? Don't even spend time on it, because you got other things to do. There's never been seen that there is such a machine that will take a certain amount of energy and put out more energy than what it takes in. It'd be nice to have. It certainly would be nice to have, but laws of nature say it can't be done. We want to focus today on work. Work is a form of energy. We define work as the force times the displacement. So in order to do work, you have to apply a force and you have to displace something. In the direction of your force. So for instance, I'm going to put somebody to work here. Let's put Einstein to work here. That's not working. So here's an object. I wish to do work on this object. I've got out of camera range. Am I in over here?
Yeah.
I wish to do work on this object here. So I need to apply force, and I need to apply it over distance to do work. So I can push on this object. If I apply force F, and apply for a certain distance D, the work I've done is to find the B, force times distance. If I apply that force in the direction that I pushed it. F times D. Units would be newtons times meters in this case. Right? If I were to approach that same object and I start pushing on it, maybe this is my job. I'm being paid to do this. Right? So you say, do work on this object. Right? Do work on this book. So I come up here and I push on this book. Let's say I push on it all day. The book is really heavy. And I'm pushing on it all day, and beads of sweat are going down my face. I'm working hard here. I'm changing chemical energy into mechanical energy because I'm pushing on this thing. So I am changing energy, and I'm eating along the way. So I have more energy, right? And at the end of the day, I've been sweating all day. I push on this object, and it didn't move all day. Now I think I've done work, right? I should be paid for that, right? When my supervisor comes in and says, "Yeah, you didn't do any work," right? Because you didn't move, right? If you apply a force and it doesn't move, in a physics sense, you have done no work. It's got to move. It's got to move in the direction of your force that's applied for you to do work. So here's two ideas. Let's say you're pushing a lawnmower and you wish to do work. Now, you have to move something in the direction of your force in order for there to be work. So if I were pushing down, or if she was pushing down on the handle of this lawnmower, she's applying a force along the handle of the lawnmower. There are two components to that force. As she's pushing down at an angle, there's a component that's horizontal, and there's a component that's vertical down into the ground. The component that she pushes with that is vertical down into the ground as this thing moves is doing no work. Because as this thing moves in the X direction, that component is in a Y direction, and there's no movement in the Y direction. So there's no work done by the component of her force that is vertical. There's work done only by the component of her force that is horizontal. So I guess if you want to have maximum efficiency in pushing the lawnmower, you might as well just get down on the ground and just kind of push it levelly, horizontally. Because any component of your force that's vertical is not doing work. Of course, that wouldn't be practical. So it's only the force that's applied in the direction that you go. So kind of looking at this, we need to modify our idea here in terms of force. Here's Einstein pushing on this block again, and he's pushing at an angle with some force F. But really, only the component that's along the direction of displacement is going to do work. And if you push it down at an angle theta, then really the force that's doing work is going to be that component F cosine theta that's actually in the horizontal direction. So the true work that he does over distance d would be the force F cosine theta times distance, or I could say in this form, force times distance times the cosine of the angle between the two directions, the direction of my force and the direction of the displacement. That would be true work. So here's a summary of this. Work equals force times distance times the cosine of the angle between the directions of the two. It's positive when the force F cosine theta is in the same direction as the displacement. Work could be negative if the component's in the opposite direction as the displacement. So let's say I decide to do work. I'm going to do work on this book again. This time I'm actually going to do some work. So I'm going to push on this and actually push it a distance. And normally if you're doing work, you're going to add energy to something. So by me pushing on this and for distance and doing positive work, I've added energy to that book. And as we'll see in later chapters, a lot of times the book will actually continue to move afterwards and have what we call kinetic energy. But in this case, it's not moving afterwards. So I actually pushed this book, and as a result of pushing that book, it did not gain kinetic energy, did not gain energy of movement. What do you think happened? Friction. And friction did work on it as well. So as I was pushing on this for distance d, there was a force of friction on it in the opposite direction against my pushing for that same distance d. And the force of friction had to be equal to my force. So as a result, it ended up with no net energy because friction did negative work on it. And the way I can do that mathematically is I could say that in terms of friction, we had a displacement that way, but the frictional force was that way. And the angle between the two of them was 180 degrees. And so in terms of that equation, I would say it would be the frictional force times displacement times cosine of 180, which is a -1. Friction did negative work. The work is 0 if the direction of the force is perpendicular to the direction of motion. The work is 0 if the particle does not move. And work is a scalar quantity with units of Newton meters, or we have a definition for the unit of energy called the joule, named after Joule. We do a lot of things with energy. So Newton meters is enough for us to define joule. So let me give you another scenario here. Here's a book here. Let's talk about work. Let's say I come over here and I lift this book up like this against gravity. Okay? To do so, I'm going to have to apply a force at least equal to the weight of the book, just maybe a slightly infinitesimal amount greater than the weight of the book, just to get it going. I apply that force against gravity, and I apply it for a distance y here. So I've actually done positive work in lifting this book up, correct? Makes sense? I've done positive work in lifting this book up like this. If I were to then put this book down, I'm still applying a force against gravity up. And now I'm going to let it displace down, like this. Put the book on the table. What kind of work have I done? Negative work. Correct. By lifting this up against gravity, force in the direction of displacement, I've done positive work. And letting this go down, still applying a force up against weight, if I'm letting it displace down, I've done negative work. Negative work in the same magnitude as the positive work that I did in lifting it up. Net result, 0 work. So I've done positive work, I've done negative work, I've done a total of 0 work. Make sense? If I were to carry this book, applying a force against its weight, so my force I'm applying on this book is basically up. And let's just say I just give myself a little impetus to start moving. But I'm applying a force up, and now I displace in a forward direction. Am I doing work right now on the book as I'm moving?
Yes.
Very good. I'm not doing work. Why? It's not in the same direction as displacement. I'm applying a force that's up, but the displacement's forward. So basically, I'm doing no work as I move at constant speed, like this. So, if I were to move something, something's on the table like that, I approach this, I've done positive work, 0 work, negative work, equal to the positive work that I did over there, at least in magnitude. Net result, 0 work. Let's say I got to move Saturday. I need some help. I need some help. I'm going to move from one house to another house. Right? And so I say, you know, you're my friends. How about come on over and help me move? And if you do work, at the end of the day, we'll have pizza and beer. Pizza and soda pop. Pizza and soda pop. At the end of the day, if you do some work, and you say, well, that sounds like a pretty good deal. Pizza and pop. All right, Dr. Golben, I'll show up. Of course, they were my true friends. They just call me Golben. All right, so everybody shows up. And sure enough, I got all the stuff out there, and I watched this take place, and people pick up stuff, and they lift it and put it in the moving van, and they put it down, and then I drive to the new location, and sure enough, pick it up and carry it on in, and then put it down in the new location, and then so at the end of the day, everything's moved, and great job, I say, hey, Golben, where's our pizza and pop? Our pizza and soda. And I say, well, technically, I mean, you did do work when you lifted this out like this, but you didn't do any work when you carried it, and then when you put it down, you did negative work, so technically, you didn't do any work today. So I don't know about the pizza and pop. You have to think about that. And this is why I don't get anybody to volunteer to help me move. There's all these technical things that I bring up. Try that one out on your friends. See if it goes off.
Could you define the work in the acceleration though?
You might do, I mean, if you actually were to accelerate in the X direction, so if you actually start out like this and you start actually applying a force so that actually you pick up speed in the X direction, you would do work, right? So the way we're doing it here, now, the way we're doing it here is that we're kind of moving at constant speed. So after the little impetus to get going, which probably was a little bit of work to get going, we also did a little negative work when we stopped, and that little bit of impetus. Yeah. There's a question in your lab, I think, where you pick up your backpack and say, do you work when you carry your backpack to school? Right? And your answer to that now would be no. Right? Because you did positive work and you picked it up, and if you walked pretty much at constant speed, you did zero work and then negative work when you put it down. Yes?
So when you accelerate, you do some work.
When you ask what?
When you do something.
Accelerate, yes. When you accelerate, you would do work, because if you apply a force on something in a distance. I should order the pizza? Yeah, I think I should. I want to have friends.
I'm probably going to hear.
Beer would be better than the pie. All right, let's try this problem. A horizontal force of 150 newtons is used to push a 40-kilogram block 6 meters on a rough horizontal surface. If the box moves at constant speed, find the work done by the 150 newton force. All right, so I have a box on a plane, and I'm going to push on it, or somebody's going to push on it. Put Newton to work, since all this stuff is his doing. We're going to put Newton to work. He's going to push on this box against friction with 150 newton force for 6 meters. We want to find the work done by the 150 newton force. Well, we actually did move it. We actually moved it in the direction of that force, so we did do work. We're sliding it, so we're not picking it up. So our force applied would be 150 newtons for 6 meters. They're both in the same direction, so the cosine angle between the two directions would be 0 degrees. So cosine of 0 is 1. So this would be 150 times 60 times 1, which is 900 joules. So in pushing this, so if you help somebody move, just push something on the ground. In pushing this, you would do work. In this case, 900 joules of work. What was the work done by the frictional force? Now, in the statement of this problem, it said that this block was moved at constant speed. So I applied a force here, and as I applied this force, it moved at constant speed. What does that tell you? If something moves at constant speed, what can you say dynamically about that object? No acceleration. And if there's no acceleration, there is no force. It's Newton's first law. So it'd be the same as if we're at a static situation, if they were at rest. If it moves at constant speed, that means there's no net force on it. But Newton applied a force, 150 newtons that way, so there are forces on it. There's just no net force on it. That means, in your mind, that the frictional force should be equal in magnitude and opposite in direction. The frictional force is canceling his force. That is a key word in reading problems of this nature, is the words constant speed. It says constant speed is a Newton's first law problem, that no net force, all forces add up to 0. So the frictional force is equal in magnitude, opposite in direction, in this case. So the work done by friction would be the frictional force times the displacement, 6 meters. When the frictional force is going this way, displacement's going that way. The angle between them is 180 degrees. Cosine of 180 is -1. frictional force has done a negative 900 joules of work. Net work done is 0. Let's use this last result to find the coefficient of kinetic friction. Let's kind of go off on the side here. Kind of back to the chapter 6 step. Find the coefficient of kinetic friction in this case. Well, there's the normal force, in this case, looking at this free body diagram, would be equal to the weight because there's no acceleration in the y direction. So normal force equals mg. So the frictional force should equal mu times that. So the frictional force equals mu times the normal force, which would be mu mg. And that's equal to 150 newtons. Solve this for mu. So mu will equal the frictional force divided by mg. 150 newtons divided by 40 kilograms times 9.8. That means the coefficient of friction in this case was 0.383. No units on that because that's always a fractional number. It's just a coefficient relating the frictional force to the normal force.
I had a question. Okay, if you're like walking up the stairs, like you're still kind of applying force, right?
Right.
Right. And like if you set it on top of something that's higher than what you started out with, you're only doing like part of the force, right? Or like
Right.
part of the work.
Excellent setup. Okay, so what's your question?
Huh?
Or is that your question?
Yeah, that was my question. So just wanted to clarify.
Yeah, actually, I'm kind of glad you said that. If I were to do that moving scenario, if I were moving from a one-story house to a two-story house, I better come up with a pizza and soda, right? Because ultimately, anything that was carried from the one-story house is carried up the stairs and then put down up the stairs had positive work done on it. Because you did work against gravity and carrying it up the stairs. You did no negative work. You did a little bit of negative work putting it down, but ultimately you did positive work in carrying it up the stairs. So a good point. So if you were upgrading, I guess, from a one-story to a two-story or five-story house, anything that goes up would be positive work. Now, on the other hand, if you're moving from a two-story house to a one-story house, then ultimately, at the end of the day, if people have done negative work, they ought to buy the pizza and pop. They have done negative work on your stuff. If we were to plot force versus displacement on a graph, and let's say the force was constant, it would look something like this. If I put x on my displacement on my horizontal axis and put force on my y-axis and plotted that with a constant force applied over a certain distance, I would get a graph that looks like this, right? The area underneath that graph would, well, work would be equal to force times displacement. If we're a constant force with a constant displacement, then constant force, constant displacement, then this times this would equal work. And that would basically be the area of this rectangle. So the area underneath the force versus displacement graph represents something. It represents work. In other words, anytime you would plot force versus displacement, the area underneath that graph will represent the work that you did. So if I had something like this, let's say I had a varying force. Let's say I didn't always push with a constant force. Let's say I pushed kind of hard at first, a little bit harder, and then softer. And I were to graph that force as a function of displacement. I might get a curve like this. The area underneath that curve will represent the work that I did. How can we figure out that area? Well, what I might do is just kind of break it up into little infinitesimal pieces. And I'm going to say that the work I did for this little infinitesimal delta x piece here is the area underneath that portion of the graph, which I can approximate as being the area of a little rectangle that goes up to that graph and goes infinitesimally over and down again. So this area here would represent the work I did over that little moment right then. And if I did that for every little moment underneath this graph, I would get the area of every little rectangle underneath that graph. And ultimately, I would want to find the area of all those little rectangles underneath that graph. So I would say I'm going to sum up every little x force multiplied by every little displacement delta x, add up all those contributions underneath this graph, and if I summed up all those together, I would get the work that I did with this varying force. Well, you have a symbol that helps you describe what that summation is. If you have an infinitesimal delta x applied from initial to final x, and you summed up all those contributions, that is called a definite integral. In this case, a force times displacement force dx. Dx is your infinitesimal displacement. So if I took the integral, the definite integral of a force of x over dx from initial position to final position, I would get the work done by that varying force. And basically, anytime you take the integral of anything, you're taking the area underneath your graph, right? So you're just finding the area underneath the graph. Let's try this out with what we call a spring force. The spring is a varying force. It depends on x. If I had a spring and I pull it out a certain x, the force gets stronger and stronger restoring it the more I pull on x. And so the force restoring it back to its original position is proportional to the position or the amount that I pull it away from that position. So I pull it out here, it gets harder and harder to pull the spring out. And for that matter, if it's a good spring, if I push it in, it gets harder and harder to push it in. The force gets stronger linearly the further I get away from its equilibrium position. So the force is proportional to x, and we have a proportionality constant, k. And we call it negative because it's always a restoring force back towards opposite the direction that you're going. If I were to plot this force as a function of displacement, it would look something like this. Force equals negative kx. So as I went in x direction like that, I would plot this force, which is a line. It's equal to the slope of negative k times x. So it would be a line going down like this. And using this idea of work being the area underneath that graph, the work would be the area underneath this graph, which is actually the area of that triangle there. And 1/2 the base times the height, 1/2 x times kx would give me the work done, which the magnitude would be 1/2 kx squared. So in a physical sense, it's just the area of that triangle, 1/2 kx squared. I could also get this result if I were to integrate my force versus x as I pushed on this from 0 to x. I'm going to push on it with the force kx from 0 to some value x. So I'm going to integrate my force over dx from 0 to x. My force was kx. K is a constant. So I'm going to have kx dx from 0 to x. I'm going to take k, the constant, out of that integral. And so I'm just going to integrate x dx. And you know how to do that. So that's going to be 1/2 kx squared. And of course, check that with the derivative of that. And integrate that from 0 to x. So you get 1/2 kx squared minus 0, 1/2 kx squared. So for a spring force, which we're we're gonna worry about that in chapter 8 a little bit more. But for a spring force, the work that you would do in moving at a distance x will be equal to 1/2 kx squared, because the force is not constant. It's proportional to your x. One last comment on this is that if I actually did work on a spring, if I had a spring, and I pushed on it and did work on it and pushed it in, and I physically have done work because I've actually moved it, all right? That energy is gone somewhere, and it is gone into the compression of that spring. And we have a word for that that's called potential energy. So now all the work that I did pushing it into the spring is now stored in the potential energy, and that spring now has the potential to do that work back. So in a sense, I've kind of stored that energy for a while. It's got potential to do work. All right. More on that later, like I said, but that's a start. And I'm going to stop there today. We'll see you, some of you in lab